Writing neutralisation symbol equations. So the first thing we have to do when we're writing symbol equations is to work out the molecular formula for the substances that we're using. You're all familiar with the periodic table of elements, and you know that they're arranged to some degree based on their electron configuration. So when we look at the groups, which are the vertical columns, we know that group 1, which is here, that has 1 electron in the outer energy level. And here, in group 2, we have 2 electrons in the outer energy level. So you've met this idea before. Now we can use this idea to help us work out how an element from group 1, like sodium, might interact and bind and balance and make a molecule with an element from somewhere else on the periodic table, like chlorine over here. So we need to know what's going on here. Now we know that this is in group 7, but when we think about electron configuration, what we also know is that it's got a nearly full outer energy level. It's just missing 1 electron. So if it interacts with sodium, it could actually take that extra electron from the outer energy level to fill up its energy level. And this sort of desire, you can't really desire something for an element, but this energetic requirement to either lose an electron from the outside energy level or to gain an electron into the outer energy level to make the energy level full is sort of the driving force of chemical reactions. And this is called the valence valency. So if we have a look at the next slide, this is the valency numbers for different groups. So you'll notice that group 1 over on the left has a valency of +1, and group 7 over on the right has a valency of -1. And we can use valency numbers to work out molecular formula. So let's have a look at how we can do that. So we can have a look at tables of valency numbers, and you'll notice that here we've got, so for example, here's sodium. It's in the left-hand column here, it's got a valency of just a plus, so it's just 1 plus, it's a 1. And here's chlorine or chloride, once it's an ion over here, it's got a valency of a minus or a -1. So when you put them together, they can just become sodium chloride with 1 sodium, 1 chlorine, and they kind of cancel each other out. And there are some interesting things on this table that you might notice. So we've got something here which isn't an element. It's actually got 2 elements together. Hydroxide has O and H, and together they act as if they have a valency of -1. And the similar thing happens here with sulfates. SO4, they as a group act together to have a valency of -2. There's carbonates, there's ammonium. There are other polyatomic ions, they're called, that have a valency, a combined valency that we can work with. But we'll meet a couple of these as we do neutralisation reactions. So let's have a think about the reaction of hydrochloric acid with sodium hydroxide. So this is a very straightforward neutralisation reaction. We know that they make a salt and water, and we can work out that the salt is sodium chloride. So let's have a look at how we work out the molecular formula. So for hydrochloric acid, we need an H and a Cl. So H is found over here. So there's our H, and that's got a valency of +1, and Cl is here. It has a valency of -1. So H and Cl easily balance each other out. So 1 of each will be sufficient to make the molecular formula HCl for hydrochloric acid. Now sodium hydroxide, just change colour so that you can see. Sodium hydroxide, sodium is here. Sodium is a 1 plus, and hydroxide ions are here. So the formula for sodium hydroxide, we've got a single plus and a single minus, so they cancel each other out. We just need a 1 of each to make our formula sodium hydroxide, Na, and then a capital O, capital H for hydroxide, so NaOH. Okay, sodium chloride. We've met these ions already, so sodium is Na+, and chloride is Cl-, so a plus and a minus that cancel each other out. So the simple formula for sodium chloride is Na, capital N, small a, chloride, capital C, small l, and one of each cancels each other out to make a neutral molecule. And we know that the molecular formula for water is H2O. So that's how we work out the molecular formula and the symbol equation for that simple neutralisation reaction. Let's try another one. So here we have nitric acid reacting with potassium hydroxide to make potassium nitrate and water. So you can pause this video and see if you can work that out for yourself, and then I will show you. So let's have a look. So nitric acid is going to need H+ ions because it's an acid, and the nitric bit comes from here, nitrate. So if you look, we have a simple 1+ and a simple 1-. So our formula is capital H, and then capital NO -3. And because we have a 1+ and a 1-, they have now cancelled each other out, and there's our molecular formula for nitric acid. Now, potassium hydroxide. Potassium is here, K+. Hydroxide we've met already, OH-, 1+, 1-, they cancel each other out. So potassium hydroxide is capital K, capital O, capital H. You should be able to have worked out potassium nitrate. Potassium we've met already is capital K. It's got a 1+, and that is easily balanced out by the nitrate, which is NO3. You'll notice I'm not writing any pluses or minuses because they're cancelling each other out, so they don't need to appear in the molecular formula. And again, we know what water is. Water is H2O. So a nice and easy way to work out the molecular formula. Just think about cancelling out our positives and negatives. So let's look at something that's a little more tricky, but we'll still meet it in our lab because they are everyday acids and bases. Sulfuric acid. So sulfuric acid, because it's an acid, it's got H+. And we've got to look for sulfate. So sulfate is down here. SO4 2-. Now, we have a little bit of a problem. We have 1+ for our hydrogen and 2- for our sulfate. To balance them out, the way we solve that is to take 2 of the H+. So we write that as H, capital H, with a little 2 next to it, sort of dropped down. And that now gives us, in the molecular formula, it gives us 2 pluses, and that's going to cancel out the 2 minuses from the sulfate. So SO4, yeah, so we've got 2 pluses with the hydrogen, 2 minuses with the sulfate. They now cancel each other out, so the molecule is overall neutral. We've met potassium hydroxide already. K is a single plus, and OH ions are a single negative, so you just need one set of each. Now, let's work out potassium sulfate. Potassium is our 1+, sulfates are here. We have the same problem that we had with the sulfuric acid, so we need to make 2 potassiums for every sulfate, so that we have 2 positive Ks to balance out the 2- that we get with the sulfates, and then water. So these are our molecular formulae for this neutralisation reaction. We have a slight problem, and I'll show you what the problem is on the next slide. So when we react an acid and a base to make a salt plus water, in this case we have a slight problem because we don't have equal number of atoms on the left in the reactants as we do on the right in the products. So let's have a quick count of what's going on. So let's have a look at the hydrogens. We have 1, 2 hydrogens, 3 hydrogens on the left, and we have only 2 hydrogens on the right. So this is a problem. We're okay with our sulfates. We've got 1 sulfate there and 1 sulfate there, so they are okay. But we have a problem with the potassiums as well. So when we go to the potassiums, we have 1 here, but we have 2 on the right in the products. So, and we have the oxygen's balanced at the moment, but we're going to mess them about in a minute. So we've got 1 oxygen here, and we have 1 oxygen over here, but we need to do some fiddling around. So basically what we're going to do is we're going to take 1 molecule of acid and we're going to react it with 2 molecules of base. So every 1 sulfuric acid molecule is going to react with 2 molecules of potassium hydroxide. It kind of makes sense when you look at the molecular formula for the acid. But let's have a look at what this does to our balancing, because now we have 2 potassiums on the left. So that matches our 2 potassiums over here on the right, so that's a good thing. We've just messed up our hydrogens though, because where we had 3 hydrogens on the left, we now have 4 hydrogens on the left, because we've just taken a capital 2, we've got 2 molecules of potassium hydroxide, so we have an extra H. So we've now got 4 H's on the left, but only 2 on the right. I can see an easy solution. We're just going to make 2 water molecules. So if we make 2 water molecules, we now have 2 extra H's and an extra O. So are we balanced? So let's just double check. Let's actually get rid of all of our little workings out. Let's see how we go. Okay, so let's start at the beginning. Let's look at hydrogen. We've got 1, 2, and then we have 2 molecules of the base, so we've got 2 hydrogens there, and we've got 2 hydrogens in water, but we're making 2 molecules of water, so that's 4 hydrogens altogether. So our hydrogens now balance on the left and on the right, which is good. Sulfates haven't changed, there's still 1 of each. Let's have a look at our potassiums. So we have 2 molecules of the base, so 2 potassiums, and over here in our salt we have 2 potassiums. They now balance. Excellent. Let's have a look at our oxygens. I forgot what colour I gave it, we'll make it green. So we have 2 oxygens on the left here, I'm not including the ones that are in the sulfate, and we have 2 molecules of water, so that's 2 oxygens over here. So that's how to balance an equation. You're going to get lots of practice moving forward, and remember, it is extension at this level.